Hello and welcome to this tutorial on acidity and pKa. By the end of this tutorial you should be confident on what an acid and what a base are, what conjugate bases and conjugate acids are, and finally factors affecting acidity including hybridization. So what is an acid and what is a base? When we think of acids and bases we think of them as being two extremes that describe chemicals, just like hot and cold are two extremes that describe temperature. In simple terms, an acid is a proton donor and a base is a proton acceptor. Now let's look at conjugate bases and conjugate acids. A conjugate base is the species left over after an acid has lost its proton. I can demonstrate this on this equation. We have an acid reacting with water to form H3O+ and A-. So clearly here, after this acid has lost its proton, it forms A-, and this is what we would say is the conjugate base. This is true for conjugate acids too. I can show this on another equation. A conjugate acid is the species formed after the base has accepted a proton. So here we have hydrogen chloride reacting with ammonia to form NH4+ and a chloride ion. Ammonia is acting as the base. When the base accepts a proton from hydrogen chloride, it forms NH4, and so therefore this will be the conjugate acid. Now let's take a look at weak and strong acids and bases. So we know that acids release protons, but the amount of protons that get released per molecule is what will determine if the acid is weak or strong. A weak acid will partially ionize or dissociate to its protons, whereas a strong acid, such as hydrogen chloride in this bottom equation, will completely ionize and completely dissociate to lose its protons. This is represented by the single arrow, which is not in equilibrium, to show complete dissociation. Now let's take a look at pH. This is the measure of acidity or alkalinity in a solution. More specifically, it is a measure of proton concentration in aqueous solution. If we take a look at this reaction here, we can get from this the equilibrium constant. This is shown as so. You can see here on the bottom is the acid and the water that react to form what's on the top, the conjugate base and H3O+. In this reaction, water is in huge excess, so essentially its concentration is constant. So it becomes part of the equilibrium constant to form the acidity constant, where water is now missing from the equation. The acidity constant is a measure of the strength of an acid in solution, and is the pH at which 50% of the acid has dissociated. We can express Ka, the acidity constant, in a logarithmic form as pKa, which is minus log of Ka. Okay, so now let's move on to factors affecting acidity. The first factor we are going to consider is the stability of the conjugate base. The more stable the conjugate base is, the stronger the acid will be. This is because if this conjugate base is really stable, then the acid is more likely to dissociate because it wants to be in this stable form. When determining the stability of the conjugate base, we look at the electronegative substituents it's attached to. The conjugate base has a negative charge, and electronegative substituents are really good at bearing this negative charge. And therefore this will make the conjugate base more stable. Let's take a look at some substituents and compare their electronegativities. So you should be aware that fluorine is the most electronegative substituent in the periodic table. Therefore, if this is part of the conjugate base, it will be the most stable. More stable than OH-, which will be more stable than NH2- as it is more electronegative, and NH2 will be more stable than CH3-. This therefore means that hydrogen fluoride will be the strongest acid as it forms the most stable conjugate base, and methane is a really weak acid as it forms an unstable conjugate base. The factor we're going to discuss is the strength of the HA bond. Let's take a look at our first equation. If we have a really strong acid here, it will dissociate and lose its protons readily. In order for it to dissociate and lose its protons readily, it must have a weak HA bond. So the weaker the HA bond, the stronger the acid. When considering the strength of the HA bond, we take a look at the substituents in the acid and the size of these substituents. Let's take a look at fluorine, chlorine, bromine and iodine. If we go down this group, we know that the atomic mass increases. Decreasing size of substituents increases the strength of a bond. We would expect fluorine to have the strongest bond, then chlorine, then bromine, and iodine would have the weakest bond as iodine has the highest atomic mass. Hydrogen iodide is the strongest acid because it has the weakest bond and so will readily dissociate its protons. This is stronger than hydrogen bromide, which is stronger than hydrogen chloride, which is stronger than hydrogen fluoride, because hydrogen fluoride has the strongest H acid bond, so will not lose its protons as readily as the other acids. Okay, the final factor to consider is hybridization. I have ethene, ethane and ethyne. I've highlighted the acidic proton that we are going to lose in blue. If you take a look at these three different molecules, what do you notice about the S character? Ethane is sp3 hybridized. Ethene is sp2 hybridized. And ethyne is sp hybridized. Increasing the S character increases acidity. This is because the s orbital sits really closely to the positive nucleus, so when you form this conjugate base, the negative electrons will be lying on that orbital and therefore stabilised by the positive nucleus. So how do we calculate S character? Simply put, S character is the percentage S of the total number of orbitals. So let's work this out for ethane. Ethane is sp3 hybridized, so S over the total number of orbitals, S, P, P, P. This has an S character of about 25%. Now, ethane, this is sp2, so S over the total number of orbitals, and this is about 33% S character. Finally, ethyne is sp hybridized, so S over S and P has 50% S character. Ethyne has the greatest S character, and so the electrons on the conjugate base will be closest to the positive nucleus, so better stabilised. Therefore, this would make the strongest acid because it is more likely to dissociate to form the stable conjugate base. As we have already discussed before, we know that an increased stability of that conjugate base makes a stronger acid. Thank you for watching this tutorial.